Okay, so the action potential, right? Now we're going to suddenly get ions crossing back and forth across the membrane. And it is going to be dependent on the opening of what are known as gated channels, channels that are actually closed. These are protein channels that traverse the entire membrane, that go through from the extracellular space to the intracellular space, that can be in at least two conformations. We're going to see one has actually three distinct forms that it can take, and at least one of them has to be closed, right, where nothing can get through, nothing can go from one side to the other. That's gated, and under other environmental circumstances, it'll physically shift its shape, its conformation, and open a channel to let specific ions go through. And the specific event that has to occur to allow for the initiation of an action potential, the opening of these specific gated channels, is a change in the voltage, in the charge difference across that membrane. You have to go from the polarization at the resting potential, which is minus 65, and you've got to bring it down to something depolarized, to what they call a threshold potential. And that's a depolarized, less difference, right? Less polarization, value of around minus 55 inside the neuron versus the outside of the neuron. If something brings that neuron down from minus 65 at rest down depolarized to minus 55, well, then there's going to be a lot of changes in the permeability of the membrane, particularly to the ions sodium and potassium, because a lot of these very special voltage-gated channels are going to suddenly swing open. And the most critical aspect is that this has to reach minus 55, right, down here at the axon hillock, at that bulge at the beginning of the axon. Because if that occurs here, if all the changes that may be happening up in the dendrites, and we're going to see some of these, you could be having depolarizing changes, opening of, let's say, sodium channels. Calcium channels will also do it, because calcium is in high concentration outside and would run inside the cell. It's in very low concentration on the inside. You could also have hyperpolarized changes out here. You could have potassium channels opening, right? Remember, potassium would leave. Another important ion that can actually hyperpolarize the cell would be, chloride. So if there were chloride channels opening, remember, chloride comes in with sodium. Sodium chloride is salt. When you salt your food, you get not only sodium ions in the exterior of the cell, but you also get lots of chloride ions, and it's in high concentration on the outside. So if you open channels, the concentration gradient force wins and it goes inside, and then you'll bring more negative ions to the inside, and that will increase the charge difference, go from minus 65 at rest, that level of polarization, say up to minus 70 or minus 75, right, before you again equalize the forces, and it'll be happy at a new equilibrium, but it would be hyperpolarized. So you have all these different changes that are occurring here. So what we're talking about in terms of the action potential, really we want to depolarize to minus 55, to what's called the threshold potential, because at that particular value of charge difference, there are going to be big changes in the number of channels, of gated channels, that are suddenly ungated and can allow for action, for ions to pass back and forth between the two potentials that you would place in an experimental setting, like stick an electrode or a potential inside and one on the outside. You want ions to go back and forth for action. You want that back and forth to propagate, to work its way down the wire. That's the message, the electrical message that the neuron's going to send. Now, if you look at this image here, you can see we have a whole bunch of what are called voltage-gated sodium channels. This is going to be super critical for the initiation, the beginning of action between the potentials. Because at minus 65, right, that's the resting potential difference. You note it is indicated as closed, right? But if you depolarize, and I put here minus 50 to minus 55, the specific value for the threshold potential difference depends on where in the nervous system you're talking, which species you're talking about, all those sorts of things. But around minus 55, let's say, that's a depolarized value, right? This channel, this is it at minus 65, right? This is the outside of the neuron, let's say. This is the inside. It's closed. It's gated. But at minus 55, this swings open like this and allows for, selectively, sodium to race inside. And remember, sodium's racing inside because at rest, it's in high concentration outside, so the concentration gradient force drives it in. And at rest, it is negative inside, right, minus 65 versus the outside. So it's a positively charged ion out here, so it also races in because of the electrical force. Now, I want you to think about what's happening. You're going to have minus 65, right, closed, minus 55 open. Suddenly, all this sodium racing to the inside. That's going to further depolarize, right, because you're bringing in even more positive sodium ions from the outside to the inside. So the charge difference keeps dropping. You keep depolarizing. It goes from minus 65, 55, it's open. And then it goes, all that sodium coming in, 45, 35, 25, 15, 5. It actually goes to 0, and it will briefly reverse the polarity. It'll become positive on the inside versus the outside temporarily because there's suddenly so much sodium that has just rushed in enthusiastically to the inside, right? And this machine, this particular channel, is going to respond to that voltage and shut. So I want you to get this sequence clear. Minus 65, the resting potential. This is a neuron not sending a message, right? We're going to have this particular protein embedded in the membrane, the voltage-gated sodium channel, closed like this. And then you hit the threshold. You depolarize. You depolarize many ways. You can push on your finger, for example. There are specialized proteins in specialized afferent sensory neurons that'll twist open a channel to let sodium go through. You're pushing here, I'm touching gently here. Well, it's allowing sodium to go in and depolarize to threshold, and then bam, it opens. If we're talking about a synaptic connection, right, where you have one neuron releasing a neurotransmitter that's going to excite or depolarize the next neuron, well, it'll bind to a receptor protein on the next neuron, and that receptor protein may open a channel to let sodium go through. And that'll allow the sodium in, reduce the charge difference, reduce the polarization, depolarize towards the threshold necessary for swinging open these voltage-gated sodium channels. And then all that sodium comes rushing in, right? When you hit the threshold, and it further depolarizes, reverses the polarity, gets up to like positive 20 inside versus the outside. And then this thing responds again to that voltage by shutting. And the thing to keep in mind is that this initial, at minus 65 at the resting potential, this particular structural conformation of this voltage-gated sodium channel is going to be different than the closed form, after you've had all that sodium rush in. So this is what happens. It goes minus 65, closed, right? Minus 55, it swings open. All that sodium rushes in, reverses the polarity, it closes. And in this closed form, it will not reopen at minus 55. In fact, you have to get back. You have to repolarize back to the resting potential of minus 65. And at that stage, this will reset to allow for another, initiation of an action potential should you then depolarize back down to minus 55. We'll keep talking about this, and hopefully this will make sense as we continue with our story.